Okay, guys, welcome to chapter 8. We're talking in this chapter all about work and machines. So I just got done listening to the new Rihanna and Drake song called Work because I thought that might help me with this chapter. It didn't really help me. It was entertaining, however. But work is, and what this section is about, work and power, are both kind of words that could confuse or mislead you if you think about them, because we use the word work and we use the word power in so many different ways, and for that matter, machines too. We kind of think about machines in really common ways. It could be kind of confusing once you hear the definitions for these scientific terms. So when we think about work, like you're a student, right? So to you, work is studying, right? You is doing mental output. You're exerting yourself as you read and you learn new terms and you study and you do math problems and you read the Bible or whatever you're doing. And when you're parents, you're an adult, you do work, right? Like there's some fake people down below in this picture here, right? That are doing their work, right? There's a doctor, a chef, a nurse, a construction worker, right? They're doing work. They go to work every day, like you do work, right? And unless you are maybe this guy, you're maybe not actually doing work. So I'll get to that in a second. And here, there's a picture of like a power button, right? So, well, why is that there? Well, power, we think about power as like electricity, turning things on, off. It runs on power. We think about it just in terms of that. Or you think about power in terms of like, a politician having sort of social power, political power, right? Being able to do things. So those definitions can lead you to the right answer, but they're not the same as the scientific definitions of work and power, okay? Which we're going to talk about in this section. So I want you to think about this question and to answer on your paper. So tell me what kind of specific work is being done in each activity. So, and then kind of like rank the activities that require the least amount of work and that require the most amount of work. So carrying heavy books home, reading a 300-page novel, skiing for an hour, lifting a 45-kilogram mass, holding a steel beam in place for 3 hours, or jacking up a car. So which do you think requires the least amount of work? So in some of these, you're not actually even doing work. The kind of interesting thing is that that is actually one of the activities that requires the least amount of work. Now, the key thing is what's happening with the bar. Is it moving? It seems to be, this question is saying it's in place, right? So if it's staying in place for 3 hours, sure, you're using a lot of force to hold it up, but you're not exactly doing work. And you'll see what that is in just a minute. So that's sort of the intro into this sort of backwards way of thinking about work. All right, so today we're going to learn about what work is, we're going to learn about what power is and the difference between the two. You're also going to be able to calculate work and power today. So work, the definition, is the transfer of energy to an object by using a force that causes the object to move in the direction of that force. Okay, key word there being move. So you can tell something's being done if energy is transferred, right? So if you are throwing a bowling ball, you are doing work to the ball, and you're transferring energy from yourself, from your arm, your muscles, to the ball. And the ball is moving. The ball has kinetic energy now. So you're passing energy from one thing to another, right? When you're hitting a nail with a hammer, you're doing work, you're transferring the energy from the hammer to the nail. When you are pulling a cart up a ramp, right? You are moving the cart in a direction. You are transferring energy from your body to the cart. So the difference between force and work. So we know what force is, right? We know force is putting an object in motion or putting something in, applying an object force or energy to an object in a certain direction. But force and work are different because you can apply force to something and it won't move. So, for example, if you push a car, you're applying force to the car, right? But you may not be moving that car. The car may be too heavy to have its brakes on. or what have you. You're just not big enough, strong enough. So you're not doing work. So you can apply force to something but not do work, because remember, to do work, you have to move the object in the direction of the force you're applying it. Okay, so if you can push the car to the point where the wheels turn and you're moving it, let's say west, if you're pushing west with the force west, then you're doing work. Okay, so for work to be done on an object, the object must move. Key thing there, the object must move. So this is in your textbook too, if you want to look at it there. Just copy it over to here. So is it doing work or not? So we have a girl pushing a cardboard box. She's pushing it in this rightward direction. The direction, the motion is also in that direction. So yes, she's doing work. So here, this girl is carrying a backpack. So the direction of the force is up, right? She's holding the backpack up on her shoulders, and she's resisting gravity. So the force is up, but she's moving right. So she's not doing work on the backpack. Okay, the backpack is not moving in the direction of the force. Of the motion. That's the key thing, the direction of the motion. So in this case here, she's lifting some bag of groceries. So again, we're lifting like we were at the backpack, but this time she is doing work because she's lifting the bag of groceries in the same direction as the force. Okay, so notice these two are the same here, because in both cases, the force and the direction of motion are the same. Okay, now she's got the bag of groceries in her hand, but she's walking again in this right direction. So she's not lifting the bag up anymore, so it's not going the same direction as the force. Now her motion is to the right, so therefore she's not doing work on the bag. All right, so a lot of times when you lift something up, you're doing work while you're lifting, but once you've got it and you're not moving up anymore, you are no longer doing work on the bag. Okay, that's why if you're holding a suitcase and you're standing still, you're not doing work on that suitcase. Now, if you start swinging your arms and start walking in that direction, you do work on the suitcase, but not until you're moving in the same direction as the force you're applying. All right, so in this case, we can see how the same amount of work requires different force. Okay, so imagine this being a hill, all right, and you're pushing a cart. If you push the cart with F1, the force of F1, up this hill this distance, you can calculate the work. All right, so work is calculated by multiplying, as we'll see in a second, the force times the distance. Okay, so we have a force here, here's the distance, that's the work. Now, if you take the same cart and you lift it up, let's say with like a pulley or some kind of like winch or something that pulls it up, right? A crane maybe. You apply a different force in maybe a shorter distance. So maybe it's more force, see how the arrow is larger, but the distance is going to be shorter. Both work out to be the same amount of work. So it might take more force to lift it up this way. Imagine like pulling up that cart over the side of the hill versus pushing up the gradual slope, right? It takes less force to push up the slope, but it takes a longer distance to get to the top. So work depends on two things, on distance as well as force. So to calculate work, again, it's force times distance. All right. The amount of work done in moving an object can be calculated by multiplying the force applied to the distance. All right, through which the force is applied. The unit we use when we calculate force is called a joule. All right, not joule like this, but joule like that. It's a French word. All right, and it's capital J is the abbreviation. So essentially, what the joule is just the Newton times a meter, right? Because that's the unit for force, right? And meter is the basic unit for distance. So work really just equals newtons times meters. All right, but we call that unit the joule. So it's not this joule, it's this joule. Okay, so if you think back to our other example, remember we calculated that work by multiplying how far it took to push the cart up that hill times the force it took to do it. And we had two different examples, two ways of getting that cart to the top of the hill, but they would have equaled the same based on a changing distance or a changing force. Okay, so Good example of this right here. If you're kind of confused by how I can get the same amount of force, the same amount of work with different distances, take a look at this. So we have a girl here. The force needed to lift this object is equal to the gravitational force on the object. In other words, the object's weight. So the weight she's got on here is 80 newtons on this weight. So she's lifted it 1 meter off the ground. So this works out to be 1 meter here. Okay. So we know the weight of those weights is 80 newtons times 1 meter means she's done 80 joules of work. So now, as you can see, it's a different color here. Now she's added on some more weight. So she's got 100. She's doubled it to 160 newtons. Still the same distance, right? So we've got 160 joules of work. So we increase the weight and increased force is needed. All right, so now let's go back to the 80 newtons of weight. She's lifting it 2 meters, so she's doubling the distance. All right, if the distance is doubled, you can see this here, 2 meters instead of 1 meter over here. Less force is needed to lift that up. It still results in 160 joules of force. Okay, so she's doing the same amount of work she is here as she is here. Okay, so in this case, there's more force. In this case, there's more distance, but both work out to be the same amount of work. Okay, so same amount of work. So I want you to point out that these two she's doing the same amount of work. Okay, so she's using more force in this one. In this one, she's just lifting it or moving it a greater distance. Okay, down here, down below, same idea. So both of these examples require 450 joules of force to get this box onto the back of the truck. So notice, he's got to lift all this up on his own. So he's got to use a lot of force to get that box up off the ground there, right? But it's a real short distance. All he's got to do is lift it up, toss it on. But over here, look how far she's got to move it to get up on that ramp. Less force to get it down on this lower part of the ramp, right? To get it up there, and less force to slide it up the ramp, but greater distance. So you see, here he's moving it 1 meter. Here she's moving it 3 meters. If you do this math, you take the the weight of the box, right, which is 450 newtons, and the weight, the required force here is less. This works out to be the same work. Okay. So what about power? So power is the rate at which energy is transferred. Okay, so it's basically how quickly you're doing the work. All right, so to calculate power, you divide the amount of work done by the time it takes to do that work. All right, so pretty simple, right? So power is calculated with capital P. So to use this, the unit here you may have heard before is a watt. So a watt is a unit of power, which is essentially just joules divided by seconds, but they gave it a more jazzy name by watt. So you've heard watts like with light bulbs, right? We know that certain light bulbs have different wattages, right? They've got like different wattage. Well, that just means how much power they take, how much power they kind of use in a certain amount of time. All right, so let's calculate some power. So a stage manager at a play raises the curtains by doing 576 joules of work on the curtain in 12 seconds. That's how long it takes them to open that curtain. What is the power output of the stage manager? You simply take the amount of work, which is 5,976 joules, divide that by the time, which is 12 seconds, and you've got 498 watts. All right, so over here, try these two just simple math equations. And if you've unpaused it and you've done both of these now, you should have, for the first one, which you're just taking, you're kind of doing the example just like you did before. You take 150 joules and divide by 10 seconds. So for this one, you should have gotten 15 watts. And for this one, you're taking 1,200 joules and dividing by 12 seconds to get 100 watts. So if you got those, good job. You can do some basic division, and you've calculated the power of something. Okay, so it's basically how quickly a job can get done, how quickly you can do the work. Okay, and this is applied all over the place, right? Think about cars, right? So cars are a really common use for this. Race cars can accelerate faster, right? So that means that they do work faster. So they produce more power. You've heard the word horsepower before? Well, horsepower is just a term used to describe the power a car can put out. All right, so here's a really good example. So it may take you longer to sand a wooden shelf by hand than by using an electric sander, but the amount needed is the same either way. All right, only the power output is lower when you sand a shelf by hand. That just means the power you put in as you sand is less, right? But you're doing that power over a longer period of time. Just imagine how long it would take you to sand like a wooden boat versus using a power sander, right? The power sander puts out more power. Puts out more work, and lets you do that work in a shorter amount of time. All right, here's a good example again. All right, so 2 piles of bricks need to be moved across the street. Mary carries 2 bricks at a time and takes 2 days to complete the job, while Elizabeth, who's driving a backhoe, does the same job in 15 minutes. So Mary and Elizabeth do the exact same amount of work. However, the amount of power expended is much different. So think about it like this. They're both doing the same job, the same work, right? They're both moving, applying force in a direction, but one of them is doing it with much more power. Okay, so if the amount of work required is 20,000 joules, if this job requires 20,000 joules of work, we can calculate the power of the backhoe. So first, let's convert the 15 minutes into seconds, which is pretty easy, right? So you just multiply 15 times 60. So it took the second young lady 900 seconds to do the job. All right. So now divide the number of joules, which was 20,000, by the number of seconds to figure out the power. Okay. So the second young lady used I can't remember her name. Used 22 watts of power to do that job, that same job that Mary. All right, so Elizabeth produced 22 watts of power. On the other hand, Mary only produces 0.116 watts of power. Thus, more power is generated the quicker the work is performed. All right, so they're doing the same work, but if you use more power, if you have more power, you do that job faster. All right, so try this. If a force of 20 newtons is acting over a distance of 6 meters, how much work is being done? All right, so for this, remember to calculate work. You just take 20 newtons and multiply it times 6 meters, right? So you've got 120 joules of work, okay? So if it takes you, let's say 10 seconds rather, to do this 120 joules of work, if you found the power, it would just be 120 divided by 10 and get you to 12, right? So in this case, it would be 12 watts. Let me erase that. That's terrible. Okay. All right. So just to review, work is the transfer of energy using a force that causes the object to move in the direction of the force. And to calculate work is force times distance. And work is measured in joules, don't forget that. Power is the rate at which energy is transferred. Okay, that work is done. And power equals work divided by time. And the unit for power is the watt, or capital W. Okay. Okay, that's about it. Take your notes, get ready for a pretty short quiz, about 5 questions, 6 questions, tomorrow morning or whenever you have me next. If you'd like to see kind of some more visuals and pretty much see the same lecture again in your textbook, you can read section 1 of the textbook, which is page 210. It's a little longer, to 215. Okay, and that might give you some more context, or just give you another chance to see it all again. Hope you have a good night, and thanks for listening.